So our aim for today is so we need to define what is the symbol of a differential operator. If we speak about simple situation, there are no vector bundles, etc., then symbol is very simple thing. You replace partial derivative by coordinate of cotangent covector with degree which corresponds to the order of the derivative. So if you have something like that, then you replace one derivative by second coordinate of covector and this derivative by. So instead of having partial derivatives, you obtain algebraic operation by multiplication by components of cotangent vector or covector. But this requires coordinate approach, and we want to speak about coordinate-free approach. So let us try to do it. Well, first of all, let me remind you something about action of please remind me about if I proved the following claim.
Yes.
Is symmetric in F. Yes? Provided M is equal to the order of L. So it was done. Very good. Well. So we skip this page and pass to the next one. So we proved Hadamard lemma. Great. So next statement is as follows. Assume we consider add of such type, but with one of functions which belongs to the square of ideal. So it happens at the point P, and one of them belongs to the square of ideal of functions which has 0 at point P0. So we consider this expression, and at least one of functions is then
P and P0 is the same?
well, it's the same. Okay, so let me erase 0. So this guy will be 0. Okay. Well, what does it mean? What does it mean? How to prove it? It is symmetric, so we can assume that F belongs to the square of ideal. So we can assume that F1 belongs to the square of this ideal. And since this thing is linear, is multilinear. So let me remind you that the square of ideal is not a product of two objects from the ideal. It's linear combination of products of. Yes. So if we speak about element from the square of ideal, it should have the form something like that: gk, hk, and sum over k, where gk and hk both belongs to this ideal. So this is typical element in the square of ideal. But since add is multilinear, I can assume that f1 is not an expression of such form. It's just product of two functions. We can assume that f1 is just g times h and both functions belong to the ideal of functions which vanish at the point P. I don't worry about sum because it's multilinear. Okay, so the problem is simplified as much as it's possible, and now we simplify it a little bit more. So we define L tilde to be add of F2 blah 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 Fm L, and you will please tell me which is the order of this operator.
1.
Yes, this is guy of the order 1. So now situation is very, very simple. So we want to understand what can we say about this guy, assuming that G and H belong to this thing. So now situation is very, very simple. What can we say about this expression provided? How it acts on sections. How it acts on sections. So what is add of L tilde? How we write it? So we apply this guy to some section, yes? Add GH L tilde. It's some operator which acts on section by specific formula. Please remind me the formula.
Или apply it to GHS
Yes?
minus GH.
Yes. Then we apply differential operator to GHS. We obtain complicated expression because differential operators here, partial derivatives which sits inside operator L tilde, will derive functions, will give derivatives of functions. So we have complicated expression. And simplest part of this expression is this one, and we subtract it. Yes, that is a definition. I want to say that this is equal to the following thing. It should act like Leibniz identity. I hope you can help. I will write something. Maybe it will contain a mistake, but you will tell me if it contains mistake or not. G times add H applied to L tilde plus or minus, we will see, add, say, G applied to L tilde and then H. Something like this. So is it true or not?
Нужен минус. Потому что будет вычитаться GH из двух штук на L словной. И нам нужно, чтобы они ушли, правильно?
I don't know. Let's try to check. What happens if I apply this guy to section? G, L tilde, H, S, minus G, H, L tilde, S. Yes? Good. Then plus, well, HS, then we apply LGS, and then we subtract, what we subtract? We subtract G outside, L tilde applied to HS. What is written here? H is Hx by multiplication in the section, and then we apply differential operator. So Hs sits inside. So let us check if, well, tilde, okay. I think it's okay. Very good, it's okay. So this is a correct formula. So instead of considering this guy, we can consider this one. Yes, very good. So now I want to, my statement says the following. If I calculate the result of application of this complicated object with this condition to any section, I will obtain 0 value. I will obtain 0 section. At one point, not in the neighborhood, but at one point. Why this guy acts as 0 at point? So let us try to understand why this thing acts as 0. We apply it to some section and calculate it at point P. What happens? There is one obvious part and one tricky part. I really like this tricky part. One of summand is 0 for some very simple reason. This one is 0 because what happens here? You calculate G at the point P, then you calculate this difficult thing applied to the section S and substitute here point P. So this guy lives separately from this one, but this thing is 0. You multiply this result of application, this operator to the section, and multiply by function. So this is 0. But something different happens here, because what you're doing, you are applying this operator, this one, to HS, and then you substitute P. Now the tricky part comes into discussion. Obviously, you can. So what is happening here? This is a function which has 0 at the point P. Yes, you take a product. So this guy has a 0 at the point P. Then you calculate something, some operator. You know that if function is 0 at some point, then derivatives can be non-zero. Yes, but tricky part is that this guy is operator of 0 order. There are no derivatives. 0 order operator, it commutes with H. So this part is equal to H times, then you apply add G, L tilde to the section sigma, S, etc. So since this guy is operator of 0 order, the function goes outside. You don't need to take derivative of H. That's why is 0 at point P. Great. Very good. So we can define a very interesting function. Very interesting function. So assume we have operator L, partial derivative operator of order M. Then we can define the following thing: sigma of L. It will be symbol. It takes as an argument cotangent vector to the manifold M. Psi belongs to so we calculate this at the point P. To cotangent space to the base manifold M at the point P. So what we are doing? So let us consider a function which belongs to the ideal of functions which has 0 at the point P, such that F modulo ideal is the same as psi. We proved the isomorphism that this is the same as cotangent space at the point P. What we are doing now, we take 1 over m factorial, add, repeat fm times, then apply operator. Apply this to the operator L. And this will be mapped from the fiber it will be element of hom from fiber at the point P of the first bundle to the fiber over point P of the second bundle. Because this guy is a bundle map. This guy is a bundle map. Since it's linear, etc. So we can specify point P here if we want to speak about this one. But we can say also that symbol can be considered as so yes, so here you substitute the same psi, but you can substitute here some different psi, substituting their different functions, but consider them as elements of such quotient. So section can be considered as a element of bundle morphism from symmetric mth power of cotangent space tensored with E1 to E2. The formula for this is given here. This guy is a symbol.
You mean that sigma of L belongs to that thing?
Yes, symbol belongs to this space. In previous notation, we can say that it's the sections of symmetric power of cotangent space tensor E1, then we take dual, and then so this is section of this vector bundle, and this is the space of bundle morphisms from this one to that one. Well, so we need to consider an example. Let's try to consider an example.
So this definition is correct because of the previous statement?
Yes. Because if you change function f by any function in the square of ideal, it has zero contribution. So that's why you look only for first derivatives of f, but we know that first derivatives of f it's not a vector, but it's covector. Okay, so now we need to consider some example. What type of example I want to consider first? Say this one. Let us consider something very, very simple, namely we consider trivial one-dimensional vector bundle over M, and the differential operator L. So this the sections of this guy, as we know, is just smooth functions on M, nothing more. So sections of one-dimensional vector bundle, trivial one-dimensional vector bundle, which is M cross C, is the same as just smooth functions on M. Well, and I want to consider differential operator, which acts on the sections of this vector bundle, so the differential operator on smooth functions. We consider simple case. Maybe I will not write M here. Let me write here Rn. Yes, let me write here Rn. So differential operator will be very simple, dxk. So what is doing? It sends function f to its kth derivative, to its derivative along the direction k. Which is the order of this operator? K? Why do you think K? How many times do you take derivative of a function? 1. It's differential operator of order 1. If you hesitate, let us...
This is one variable.
Yes, it's... Otherwise, I will have here K. So, let us check... let us check that it's differential operator of order Well, so not good to write here function f, yes? It's good here, it's good to write here s, sign for section. So s, it is a section or smooth function. So what we need to check, that adjoint of f is a zero order, yes? Let's check it. So what is happening here? L f s minus f l s dfs along xk minus f ds dxk, and you see that it is just product of section by some function, by this function. So this operator is of zero order because it sends section to product of section by function. So it is a C infinity linear operator. So no problem. So it's operator of zero order. Very good. So let us calculate the symbol. How to calculate the symbol? In this way, we're doing things. Find the function. Function on Rk such that differential of k is exactly psi k times dxk. So I represent the covector by differential of some function. Rn, sure, Rn. Yes. Okay, k is fixed, so let me write here I. Find the function such that, so, and now you will calculate this guy. So to calculate the symbol of this operator applied to vector psi, this is a linear operator, it should act as follows. We take a section, and let's calculate where it goes. We need to calculate add f of L and apply it to the section S. It is already calculated, it's given here. We already calculated it. It's exactly psi k times section. It's exactly correspond to that statement which I gave you in the beginning of the lecture, that a symbol replaces partial derivative by multiplication of corresponding covector. As you can guess, if you write here some combination of partial derivatives, you will obtain here some polynomial expression in xi's. To be more precise, so let L be the following thing, di, and here we write dxi. What is written here? I is multi-index, a1, blah, 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 an. And then we write this expression, dxi. It means that we take dx1 to the power of a1 times dxn an times. What is the order of this operator? What is the order of this operator? Yes, it's just this number. What is the symbol of L applied to psi? It's monomial in psi. Which one? This one. Psi1 to the power a1, blah, 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 psi n to the power of an. That's all. Very good. Okay, now we calculate symbol of Theorem differential and symbol of covariant derivative. Let's try. So what we consider differential operator, which is equal to Theorem differential which sends differential forms of degree k to the forms of degree k plus 1. And let us calculate the symbol. What we should do for that? So symbol of L applied to psi is sending the form omega to something else. What is it? So we need to calculate the following thing. Add f L, apply it to form omega, and then calculate at the point P. So the calculation of the symbol is point-wise. If you want to calculate symbol at one point, you use the ideal of functions which has 0 at this point. If you want to calculate this guy at some other point, you need to consider functions from other ideal. That's why I wrote here point pi, and to be precise, I also write here point pi, because I calculate the symbol at the point pi. At another point, I use another representation, another function. But the formula which I will obtain now it will be point independent. So let us calculate this. What is happening here? So we take differential of what? Function times omega minus f differential of omega. Then we substitute the point pi. Okay. What is written here? By Leibniz rule, this guy expands into two summands. One cancels. We obtain this, and we need to calculate it at the point pi, correct? And here we see psi instead of differential of f. So this is just psi omega at the point p. So I used point p for the calculation, yes, but result is global. Symbol of the Theorem differential calculated at point psi acts as follows. It takes argument and sends it to exterior product with psi considered as one form. Okay? Okay? You can guess what is the symbol of covariant derivative. Again, I apply it to the section S. What should I do? I should do the following. I should calculate add f nabla, apply it to the section, and then calculate everything at the point pi. So this is a covariant derivative of what? Fs minus f nabla s, substitute here point p. Please make the calculation in mind. What happens?
Psi times s.
Yes, sure. Because then you calculate covariant derivative of this guy. First summand will be then you put f outside. This cancels this one. Another summand is then you take a differential of f. Calculated the point pi, but you obtain a point pi free independent expression now, because this expression is universal for all points. So symbol of nabla of psi is just, it sends something to tensor product with psi. So this is the answer.
So the symbol doesn't depend on this connection itself?
Yes. It's very simple, because any connection, any two connections, has the same part which contains derivatives and different part which contains linear operator. Well, connection forms. So connection contains two things, derivatives of psi and linear operator applied to psi's. So this is explanation why. So this formula says that all connections contain this part with derivatives. Okay. So let's go. Now we need to come closer to the most important operators for our lectures. These are Dirac-type operators. Statement. There are many operators, there are many symbols. We need to understand what is the structure of all that. So the first statement is as follows. For any C vector bundle. So what I want to say, this is kind of classification theorem for partial derivative operators. So I want to say what is the building blocks for them. It's more or less simple structure. So we start from this statement. So if we have some complex vector bundle, then there exists a differential operator, M order differential operator, say Lm, which sends section of E to sections of what? Symmetric power of cotangent bundle, M symmetric power of cotangent bundle to the base tensor with E, so bundle over M. With symbol which is identity. Let me explain what happens. I have a vector bundle. I want to write a differential operator which sends section of the vector bundle E to sections of this vector bundle. It's much more complicated. It consists of sections of this thing and that thing. But then you consider a symbol. It's a map from where? From sections of. So you need a place to substitute cotangent vectors. So it's symmetric power of cotangent to the M. How I wrote it. Let me write it in this way. Or you can think that these are just partial derivative operators of zero order. So it is a map of two bundles. Morphism of two vector bundles. So this is a statement. So we need to construct this differential operator. It can be done in a very simple way. Proof. First, choose a connection on E. I will denote it by nabla. Second, choose a connection nabla M on M.
Это какой-то кошмар. А у нас мы смотрим касательное расстояние именно на M или у нас на базе? На базе, да?
Так M и есть база.
Сейчас. Все, хорошо.
Там просто
Да.
в хоме, в первом аргументе тензор умножить на E.
Sorry, yes. It's not possible to take a tensor product of vector bundle with manifold itself. Yes, it's just E. Yes. Thank you very much. So we take a connection on E, we take a connection on M. So connection on M induces connection nabla M on cotangent bundle. For example, you can choose Riemannian metric here, then choose Riemannian connection on tangent, and induce connection on cotangent, etc. Then we define connection nabla K on where? For simplicity, I will write it in brackets. They induce connection here. So you have connection on cotangent vector bundle, you have connection on E, so we know how to induce connection on this tensor product. No problem. Now I want to ask you, what is the symbol of this nabla K? Applied to cotangent vector on manifold M. What do you think?
Composition of symbols.
No.
Some code.
It's just connection. One simple connection. Yes, it's just tensor by Xi. Well, I had an intention to sweep page back. So in this place, I calculated symbol of connection. There was no restrictions on connection. And one of you asked me, it's a kind of miracle. I take any connection and the symbol is equal to this one. It is true. Nothing wrong here. So each Xi K has this symbol. But now we consider a composition. So what happens then? We take nabla. Nabla sends sections of E to sections of this vector bundle. Yes? Then we take one connection that sends sections of this guy to sections of this guy. Okay? What is the connection which can be applied to the sections of this vector bundle? Nabla 1. Then you apply connection, you obtain new copy of T star M here. So that's why the here is square. And we can do it many times until we arrive to the sections of T star M tensor product of M, E. Tell me please, what is the last covariant derivative? M minus 1, correct. Oh, very good. So what? So we take a composition. We have a composition. And what is its symbol? Very difficult question. Actually, we need an exercise. It's a very simple exercise. I never mentioned it before, but let me mention it now. If you take a composition and calculate its symbol, then it's just composition of two symbols. This is a linear operator, and this one is also linear operator. This is tensor product by Xi. This also is tensor product with Xi, blah, blah, blah. So we have here operation of such type. Very good. But it's not what we wanted, yes, because we wanted to arrive to symmetric power, yes? And we obtained just just what? It's just tensor product. What to do?
Произведение отобразится. Перемножить.
Какое произведение?
Мы хотим от тензорной степени избавиться, правильно?
We want to arrive to symmetric power. Very simple, just take symmetrization. So tricky part is you have symmetrization, which sends T star M to the tensor power M to symmetric mth power of, it's bundle map, nothing difficult, yes? You take section and you symmetrize it, it's just linear operator, just projector. Very good. So what you're doing? So symbol of this guy is which one? It does nothing because there are no differentiation. It coincides with symbol itself. Yes? So now you do the following. You do the following. You consider composition of two operators. So you take this guy, and after that you apply symmetrization tensor product with identity on E. This is the formula for our operator Lm. And you can guess that each symbol is exactly identity. Symbol of this Lm is just it. Okay, let's go back. What happens then you calculate symbol? Each appearance of partial derivative give you one copy of cotangent bundle. So if you have operator of zero order, you have no this object here. So the symbol is identity. Symbol coincide with the operator itself. Xi has no contribution. Very good. Let's go. Let's go. Next statement is, now I can construct, so if you give me a symbol, I can give you an operator with this symbol. For example, if you speak about, case, then we have Rn as a manifold. Then it's quite simple. You give me a polynomial in Xi, and then I write a differential operator. Say, if you say me, okay, you have 7 Xi1 squared, Xi3. I say, okay, no problem. This is an operator. 7d3 dx1 2 times dx3 1 time. So if you give me a symbol, I give you differential operator. This is absolutely trivial when we speak about in this situation. But in general situation, let me write the following statement. So assume we have a symbol. What is the notation? S belongs to, so home from one vector bundle to symmetric power of cotangent bundle to the base manifold tensor E2. So it potentially can be a symbol of L, which is partial derivative operator of order M from E1 to E2, such that its symbol is exactly what is written here. Is it?
I think the symmetric part should be in the first argument.
Yes, that's correct. How to write it to erase as small number of letters. Okay. Okay. Yes? Everything else is absolutely trivial. What you're doing. What you're doing. Let us consider Lm, which is partial derivative operator from E1 to mth symmetric power of tensored with E1. We already know that we have differential operators such that its symbol is identity. Yes? Guess how to write the formula for L. One line. Hmm?
L sigma L1 sigma L plus sigma.
No plus.
Apply S.
Yes, just you to consider composition. So L is defined by composition of L with this linear operator. Because then symbol of this guy, of this composition, will be composition of two symbols, of symbol of linear operator and symbol of differential operator. Symbol of linear operator is the same as operator itself. No xi applied. And all xi's sit here. And they give you everything you want.
So can you repeat this?
Which one?
L.
So we define L to be, sorry. It wasn't correct, thank you very much.
The
So,
question is why it is a partial derivative.
because this one is partial derivative and this one is linear operator. Composition of partial derivative operators is again partial derivative operator, and its order is no greater than sum of orders of operators.
Does connection is the only thing that comes from tensoring with psi?
Sorry?
Does connection is the only thing that comes from tensoring with psi, with this symbol?
There is another statement. Next one will be the answer to your question. Very nice question. Proposition. My statement is a little bit more interesting than yours. Let me explain. Consider some partial derivative operator of order 1 from E1 to E2. The question is how it behaves, how it looks like. So assume the statement is as follows, and there exists bundle map. Oh, sorry. For any connection, for any nabla on E1, there exists a linear bundle morphism from where to where? From E1 to E2. Bundle morphism. So what, let me repeat. So if you have a bundle morphism, it defines map of sections. Sections of this guy to section of this guy. And this operator on sections will be linear over functions on the base manifold. It's a very strong condition. So such that our operator can be written as the following sum. We take connection. Then we take symbol, and we take composition. Let us have a look at the first summand to understand what's happening. So we have sections of E1. Nabla sends sections of E1 to sections of tensor product of cotangent vector bundle to the base manifold tensored with E1. And the symbol, since this guy is a differential operator of order 1, it's already symmetric power, so symbol sends it to sections of E2. So this is an answer to your question, that if you have a symbol psi tensor with something, yes, it is the same as connection plus some linear operator. So this guy contains no derivative, so if you want to, the symbol psi tensor with section comes from covariant derivatives. Well, let us prove it, how we do it. Very simple proof. We have two partial derivative operators of order 1 with same symbol. L and symbol of L composition with nabla. They have the same symbol. So their difference is a bundle morphism. It's because it's operator of zero order. L minus sigma L composition with nabla belongs to partial derivative operators of zero order. Define T to be equal to L minus sigma of L composition with nabla. That's all. Okay? So what does this trick allow us to do? We can take an operator of great order, take its symbol, then construct differential operator with the same symbol by using linear bundle maps and covariant derivatives iterated many times. Yes, and we subtract one from another, we obtain operator of smaller order. Then we repeat this procedure until we arrive at zero order operators. So the principle, so arguing by induction, we obtain the following, that any partial derivative operator is a sum of compositions of connections and bundle maps. But at intermediate steps, you can obtain complicated vector bundles. For example, here we discuss representation of this operator of order 1 as a sum of two objects bundle morphism and linear and composition of something, yes? But these two operators involve some more complicated vector bundle in the middle, this one. So if you want to start from sections of E1 and obtain sections of E2, and your operator is of order M, then in between you can obtain some vector bundles of more difficult structure than this one. But nevertheless, it looks more or less understandable that any partial derivative operators is a sum of what? Of compositions, of connections and bundle maps in different orders. That's all. So that's very simple structured things. So building blocks are very simple. Connections and bundle maps. Okay. So we have time and we can speak about formal adjoint. Do you understand why I'm saying about formal adjoint? Oh, very nice question. Adjoint of what? Okay. So we speak about differential operators from sections.
Because we haven't discussed convergence and such things.
Yes. Let me give a definition. Assume we have.
We do not worry about closure of image.
Sorry?
If we do not worry about closure of image of differential operators.
Oh, very good idea. So assume we have two vector bundles. And E1, E2 are equipped with fiber-wise Hermitian metric. So if you have two sections, then you can calculate its scalar product, fiber-wise scalar product, and obtain function. M is equipped with Riemannian. So we have Riemannian metric, we have connection on M, and what is important for me, we have volume form on M. Volume form. Then we can consider an operator from sections to sections. And now we say that L star is a formal adjoint to L if and only if for any sigma which belongs to sections of E1 and tau which belongs to sections of E2, we have the following formula. We obtain L2 sigma and we obtain now sections of E2. Then we take Hermitian product with tau. So we take the scalar product in fibers of E tau. Tell me, oh wait, I should wait a little bit while I fix.
Вы пишете?
Please repeat the sentence.
Sorry?
The sentence L star is.
Formal adjoint to L if, oh well, for any. And then I write a statement. It's not finished yet.
This is the definition, yes?
Yes, it will be definition, да, definition.
На блок вы пишете связанность Юрьевич в касательной
Да.
касательной согласования.
Да, но если она нам понадобится, она у нас уже есть.
Gamma zero. С компактной носителем.
Yes, compact support. This was my next question. The question which I want to ask you now, what is this? What is the object which I wrote here?
This pairing is a function.
What is the nature of this object? Is it a number? Is it a function? Is it a linear operator? Everything is a linear operator, okay, but
It's
maybe...
either a function or a number.
If you change the base point in the base manifold, the thing changes. So this is a function on M. And I hope that it has compact support, because tau has compact support. So I can take integral over M with respect to volume form. If M is compact, then no problem. We can consider arbitrary sections. So this is the left-hand side, and right-hand side is as follows. We send tau back to the sections of first vector bundle, obtain another function, and take an integral. And now we ask that these two guys are equal. These two integrals should be equal. This is a definition of formal adjoint. So what is the problem? Why we say about formal adjoint?
Потому что это линейный оператор на вообще, кстати, очень страшно.
So what? Formal adjoint is defined in functional analysis in a very specific situation. If you have... Что? So if you, let us remind us, if we speak about infinite dimensional vector spaces, so Hilbert spaces, yes? H1 to H2. So it has formal adjoint, yes, from this one to that one, and we can define it, blah, 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 and so on. But these guys are not Hilbert spaces. Sections, smooth sections, they're not Hilbert spaces. To obtain Hilbert space, we need to do something. We need to make it complete with respect to some norm, and crazy things will happen. And then you will see, so rigorous discussion requires the discussion of Sobolev spaces. Much more interesting. Hodge theory is based, it is a simple part of this, but we face very big difficulties, because to speak about... So, actually what I want to say, I have a differential operator. It has kernel, collection of sections which are sent to zero. I want to discuss dimension of the kernel. And also I want to consider image of this operator here. And I want to discuss co-kernel, dimension of co-kernel. And since we speak about very unpleasant spaces of sections which are not equipped with norms and something else, then I cannot say if these two numbers are finite, maybe they're infinite dimensional. So, to be honest, I need to say that at some point I would make a reference to theory of Sobolev spaces, which gives me very nice answer. But we have no time to discuss. I like this theory, but we have no time to discuss it. So it starts from sections to sections, but we need to introduce collection of norms here, collection of norms here, some maps, and etc. And then find that for some specific operators of very nice nature, kernel consists of smooth functions. It's a difficult statement that you consider Sobolev spaces and differential operator, and it appears that kernel consists of smooth functions, not L2 integrable and something else, but smooth functions. Okay, just forget it for a while, but pay attention that formal adjoint is statement that is formal adjoint. It's essential. It's essential. Okay, so How many formal adjoints one operator can have?
At most one.
Yes. L has at most one formal adjoint. Maybe not at all, but not greater than one. Stupid statement, L1 plus L2 formal adjoint. What can you say about this statement? It's okay, but the statement is another. Statement is as follows. If L1 and L2 has formal adjoints, then their sum also has formal adjoint, which is given by this formula. Because we know that some operators has formal adjoint, some not. So this statement should be understood as follows. If these two guys exist, then this one also exists. Very good. Guess what is the statement number 3? Composition, not a product, but composition. I was thinking to write the formula in correct order, but I regret it immediately. So you know that star changes the order of operators. The same statement, if these two guys exist, then we have existence of this formal adjoint to this composition.
By the way, L star sends gamma E2 to gamma E1. We never said it.
Thank you very much, yes. Okay, fundamental examples. Again, we consider very simple vector bundle. Sections are just smooth functions in M. Why I wrote M here? Okay, M. And we have vector field. Then there is a differential operator. So in previous example it was Rn, yes, and this was a just constant vector field. But now I want to consider arbitrary vector field. And then I can define the following operator, dv, which sends function, not function, function, which I wrote as a section to derivative of the section along vector field v. The question is, what is a formal adjoint to this guy? It will be an exercise for you for Friday. dv star. Well, you can imagine that you need to take a differentiation by parts, yes? So what is a scalar product? It's just product. You have two functions, just two products. So you need to send one derivative from one function to another. So it's not a miracle that you have here minus dv. So this, but integration by part contains two summands, yes? Two summands. Second one is very nice. Minus divergence of the vector field v in the metric G. For those who do not know what does it mean, please give a definition. Actually, this is just a term which measures difference between these two things. It's in Euclidean coordinates, it's usual divergence of vector field. But if you pass from Euclidean metric to some arbitrary system of coordinates, then metric contributes to this divergence. Okay. So this, yes. Let us calculate what is another exercise, but more interesting maybe. So if we have differential operator which sends k minus 1 forms on manifold M to k forms on M. Exterior derivative. It also has formal adjoint. Let me try to write from the memory. Nk plus n plus 1 star d star. Star is a Hodge star operator. Yes, it's a miracle. I remember. Sorry?
It's again divergence.
Which one?
Star, D star.
If you apply it for the vector field, yes. But now we want to calculate. Yes. So this is a formal adjoint to D. Prove it. It is the exercise. For this purpose, you need to understand what is a scalar product of differential forms, what is a star operator, blah, and everything else is trivial. Just to understand definition of scalar products, because formal adjoint requires you to choose scalar products here and here, and they should be defined by Riemannian metric here. If you took some other scalar product, then the formula will be different. With matrix induced by G on M. Otherwise, the formula will be different. Well, another exercise. Connection also has formal adjoint. But to be more careful, I will write here that I take covariant derivative along vector field V. Not just differential operator which sends something, but in this way. I want to write it in this way. And it is very, very simple. Minus nabla V. It's not a miracle because, again, you need to take integration by parts. And again, you have the same summon there divergence of vector field V in metric G.
Но если это упражнение сделать, то сделается.
Конечно. Obviously, because this is a partial case of this one, because partial derivative is a covariant derivative on trivial vector bundle, obviously. Well, we have something. Okay, we have something to say. A couple of. What can we say about symbol of formal adjoint operator? Also an exercise. The answer is the same. They are more or less the same. You need to take. So this is a linear operator, and this one is formal. It is a joint operator in a sense of linear operators. But it contains minus 1 to the power of m. It's obvious why we need to write it. Look here. These two guys are the same. So this is an operator of zero order. You don't look at it because it does not contribute to the symbol. So if you look to the symbol of this guy, it has different sign with comparing to the symbol of this object. Well. Yes, L belongs to partial derivative operators of order m. Otherwise, nobody understands what is the meaning of the letter m. Well, formally self-adjoint operator.
But in definition of sigma L star, we need to take dual of E1 and E2. E2 and they're taken with respect to the Hermitian form. You said that sigma L star is defined as a joint as for linear operator, right? And we have symmetric power m of tangent bundle.
Let me think about it. One moment. Let me think about it.
Then we switch arguments in whole.
I guess the tricky, this is a very nice statement, question, but I think that we need to understand this formula in the following way. Both vector bundles are equipped with Hermitian metrics.
That's what I'm asking.
Yes, that's why you can think that it's not from duals, but from themselves. So then we speak about what is a self-adjoint operator, which coincides with its own adjoint. In functional analysis, people say much more interesting that they have the same domain, blah, blah, blah. So there are much more, you need to check much more things than just this formula. What is the formula of self-adjoint operator? Simple cases, simplest examples. Simplest examples. How to construct self-adjoint operator? Formally self-adjoint operator.
You take formally self-adjoint and make Friedrich's extension.
No. You take one operator and take its composition with its formal adjoint in this order and in this order. Both of them must self-adjoint, formally self-adjoint. If you look at this thing, this is a partial derivative operator of which order? Since we are closer to the end of lecture, my questions became more and more stupid. What is the order of this operator? Second, because it contains derivatives here and derivatives here. We can guess that they do not cancel, so it's... And tricky part is that is a partial derivative operator in the section of the same vector bundle, because it sends some there and this guy sends back. So this is partial derivative operator, second order on sections of vector bundle E. This has a name. It names covariant Laplacian. What is the symbol of this guy? Oh, sorry. Symbol of the covariant Laplacian. It's quite simple. Symbol of this guy is tensoring with psi. Yes? Symbol of nabla star. What's happening? So you take, you calculate it on psi. So what you're doing, you take psi and calculate its square of its norm in the Riemannian metric on manifold M itself, and add minus here. So this is a symbol of this guy. So now we can finish our lecture by giving a couple of important definitions. Generalized Laplacian. Is any operator such that its symbol it's partial derivative operator of order 2 on vector bundle E such that its symbol is this one, like this one. Okay, and now let me introduce very important guy, Dirac-Type Operator. I will try to discuss with you how to calculate symbol of very specific type operators, of these type operators, because most important applications are for operators of such type. It is an operator which belongs to partial derivative operators of order 1 from sections of one vector bundle to sections of another vector bundle. It's important, from one to another, such that if you write here two compositions, this one and this one, both are generalized Laplacians. The examples will be on the next lecture. So we have 3 or 4 exercises for Friday and some exercises which are left from previous discussions. So I want to finish those exercises which are left from previous lectures and to solve 3 or 4 which I gave you today. Well, thank you very much. That's all for today.